All right, good afternoon, everyone. So last class, we were talking about the 12.2, which involved double integrals over type 1 and type 2 regions. So we first talked about double integrals over rectangles. Then we talked about a type 1 region and a type 2 region. I was able to do an example or two of that. And we also had this really nice formula for finding the area of some region, and we'll revisit that a little bit later. But there were a couple of problems that we did not do that I wanted to go over, and then we'll move into the next section. All right. So this was the first problem. It says find the volume of the given solid. And the solid is, we're talking about, okay. We're talking about the solid that is enclosed by the paraboloid z equals x squared plus 3y squared, the planes x equals 0, y equals 1, y equals x, and z equals 0. So we're trying to figure out the volume of that solid. So I think the hardest thing in a problem like this is just figuring out what you're looking at, like what the solid actually, visually what it is. And so I think you want to look at like two different ideas in terms of pictures. You want one picture that's going to be your domain, and that's going to be in two-dimensional space. And then you actually want to look at the solid, if you can, and that'll be in three-dimensional space in R3. Okay, so let's start with the domain, and that would be your restrictions on X and Y. So let's start by looking at all of these different equations and seeing if any of them are represented here on our XY plane. So how about X equals 0? Well, that's the Y-axis, right? So that's the Y-axis here. All right, we got that. How about Y equals 1? That's here, right? That's a horizontal line. Goes through 1 on the Y-axis. Now remember, these are planes. So like in three-dimensional space, these planes are coming up straight up out of the page, right? They're coming like right out at us. And so both the blue and the green, just imagine them coming straight up from the page, right? What we see on the XY plane is just these two lines. Let's see, what else do we have? Y equals X. Well, that's the diagonal, Y equals X, which should look like this. Again, that's a plane that's coming straight up out of the page. And then Z equals 0. Now, Z equals 0 is hard to draw on here, but we should all be comfortable with the idea that this right here is just the XY plane. Right, that's this whole picture, this sheet that we're looking at, right? So we're trying to find the solid that is enclosed by this plane, the blue plane that comes up out of the page, the red plane that comes straight up, the green one that comes straight up, and then the plane itself, XY, is actually one of the boundaries also. So do y'all see this region here as being our domain region? It is what is enclosed by all of those. Yes? Okay, now we need to see what does this look like? Okay, so what does this thing look like? So we need three-dimensional space to visualize that paraboloid. And this goes back to when we talked about quadratic surfaces. And what if you have the X is squared, the Y is squared, the Z isn't squared, we have an addition sign between them. This is way back in chapter 10. And hopefully you're comfortable with the idea that this looks like a bowl, like a parabola that opens up. And it's a little wider in some places than the other. So it's not like a perfect circular bowl like this. It's more like an elongated, let me exaggerate it. It's more elongated like that in one direction. But that's what we have, okay? And this is a surface, it keeps going forever, right? Up and up and up. Now, that's not the picture I want to draw, okay? I want to try and draw this picture on an XYZ plane or XYZ axis. So here comes my picture. I'm going to put X here, Y here, and Z here, following the right-hand rule. I'm going to try my best to draw this picture over here. So let me, maybe I should have done this in black. Yeah, let me do that in black. Okay, so let's start. The green is the y-axis. So that's this, right? And then the blue is parallel to the x-axis. So the blue comes like this. Oh, man. And then the red one should kind of like go through an angle through the origin like that. And then I have my little region here on the ground. And then above that, I have my paraboloid, which goes up, whatever, comes down like that. So we're trying to find the volume of the solid that is enclosed by the paraboloid. So vertically, up and down, the Z is stuck between the paraboloid and the ground. Because remember, this says Z equals 0, that's the XY plane. So the ground is one boundary. The paraboloid is the other vertical boundary. And then these lines, which again are planes that go straight up, create the sides of the solid. So do y'all see how this inherently is difficult to draw and kind of like grasp? Y'all see how that's tough? I'm going to try and draw it. Here we go. I'm going to do my best here. So let's just take these like some points. I have like 3 important points. Those are the 3 like vertices of that triangle. The first point is going to come up and hit the paraboloid somewhere. And then this back point is going to come up and hit the paraboloid somewhere. And then this point at the origin is just going to be at the origin of the paraboloid. So we've got some object that's in here like this. Man, it's really hard to see. Now I can show you what it looks like with a computer, but again, does that help you solve the problem? I'm not sure. Maybe I'll show you the picture after. Do you want to see it now or after? It's up to you.
After.
After? Okay. So let's start with the idea of the double integral. We want to see what type of region this is. Okay, so let's look at our region over here. What type is this? It's not a rectangle, right? It's not a rectangle. So it's either type 1 or type 2.
It could be either.
It could be either, exactly, because if you look at it from one perspective, the x's are stuck between 2 values, right? X is stuck between 0 and 1, and the y's are stuck between 2 functions of x. Or if you look at the other way, the y's are stuck between 2 values and the x values are stuck between 2 functions of y. Now I'm going to go with type 1. I'm going to look at this as a type 1 because I can tell by looking at it that my x's are stuck between 0 and 1 and my y values are stuck between, what are they stuck between? So what's the lower boundary of this yellow region? The red line, right? Which has the equation y equals x. So x would be my lower boundary. And then my upper bound on that yellow region would be the blue line, which is constant 1. So what we're doing from last class is we're saying our x is stuck between 2 numbers, a and b, and our y's are stuck between some function of x, g1 of x, and g2 of x. So this is this, and this is this. Now, according to the notes from last time, if we are trying to find, let me get back to this. If our x is stuck between two constants and our y is stuck between two functions of x, then this right here, this double integral would give us the volume under some surface above that region. But we want the volume between two surfaces, which is the next formula right here. If we have a domain on the ground that's type 1, we have a bottom function g and a top function or bottom surface and then a top surface, then the result is, or the volume would be this double integral right there. You're just going to subtract, you're going to take the top surface and subtract the bottom surface and then do the double integral. So we need to figure out what's the top boundary and what's the bottom boundary from our picture. So from this picture, what is the f of x, y that creates the upper bound of our solid? What is it?
That x squared plus 3y squared?
Yeah, it's this paraboloid, right? Solved for z so that we can look at it as a function of x and y. So it's just x squared plus 3y squared. Now, what's the bottom of our surface? The g function.
Zero.
0, because that is this thing right here. Right there, right? Z equals 0 is the bottom. So without any real great pictures, I mean, these pictures aren't bad, but we should be able to figure this out. The volume should be the double integral over this region D of the f function, the top surface, minus the bottom surface with respect to area. Now for us, because it's a type 1, the order of integration matters here. We have to do the limits on the x first, then the limits on the y next. And now the upper surface, which is x squared plus 3y squared, minus the bottom surface, which is 0. I don't need to put that there, but I'm just trying to stress where everything comes from. And then the dA turns into either dx dy or dy dx, and that depends on what type region you have. Here I put dy dx because the x's have to be on the outside and the y restrictions are on the inside. Questions?
Can you repeat the last part that you said as to why you did dy dx in that order? You said
Yes. Okay, so when you have a type 1 region, your x's will always be between two constants. Type 2 region is the other way around. But for a type 1, the x's are between two constants, which means that the integration with respect to x has to be the outside integral. Okay, and then the other restriction on y, that's between two functions of x, that must always be your inner integral. So whatever's constant in the problem, whatever's held between two constants is always the outside, and whatever's between two functions is always the inside one.
Thank you.
And then now we just work through this, right? We just work through this. So I'll go ahead and do this one. We're going to go integral 0 to 1. Let's go ahead and figure out the antiderivative of this with respect to y. So we treat x's like constants and y's like variables. So the antiderivative of x squared is just x squared y. The antiderivative of 3y squared is just y cubed with respect to y. And we're evaluating this from y equals x to y equals 1. And when we're done with all that, we will integrate again with respect to x. This is integral. I'm going to take this one all the way. Integral from 0 to 1. Okay, we replace all our y's with 1, then all our y's with x's, and we subtract the two answers. Fundamental theorem of calculus. Okay, so y goes in, I replace all my y's with 1, I get x squared plus 1, that's nice. Replace all my y's with x's, I get x cubed minus, is that x cubed minus x cubed? Hey, that's nice. Those go away. So now we have, I need more room here. We have integral from 0 to 1 of x squared plus 1 dx. That can integrate easily, 1/3 x cubed plus x evaluated from x equals 0 to 1. And if we plug 1 into this, we should just get 4/3. And if we plug in 0, we get 0. Any questions? Sure. So the volume of the solid that is enclosed by this paraboloid in these planes is 4/3. Let's look at it. There it is. All right, so here's the ground. Now, I apologize, this is kind of twisted. It's not the same direction as it was when we drew it. But here's our paraboloid. All right. Here's x equals 0. Remember, x equals 0 was one of our boundaries, and that's a plane. Let me take the paraboloid, let me get the paraboloid out of here. Oh no, they have to both be there, sorry. So there's the x equals 0. Here's the ground, z equals 0. Here's y equals x, that diagonal one. And then we have the next one, which was y equals 1. See, it's a complete mess if you try and draw it. So we're looking like from the top. We were looking at it like from here, like this. And we're looking above that region, and we're trying to figure out, let's see the top. Let me twist it around so we can see it. Oh my goodness. So the top of our solid is bounded by that surface, and the bottom is bounded by the XY plane. So here comes the solid. It's right there. It's that thing right there. Now this all gets in the way, so I'm just going to pull all the boundaries out. Give my computer a second. It's thinking. So we found the volume of that solid right there. And that volume is 4/3. So here's it from the top. And then, you know, from any different side, we can see it. So do y'all see from this picture right here, how the paraboloid created the top boundary of the solid, right? And then the bottom of it was just the XY plane. So that was our F and our G. And then everything else was just our type 1 region on the ground. Okay, I hope that makes sense. Does it kind of make sense what we just did? Let's try this next one. Okay, find the volume of the given solid bounded by the cylinder y squared plus z squared equals 4, the planes x equals 2y, x equals 0, z equals 0 in the first octant. Okay, let me try and draw. So here's my 2D, here's my 3D. All right, let's talk about the ground. We've got on the ground here x and y. All right, let me start with the easy ones. X equals 0, right? That's the y-axis again. Z equals 0. Well, that's the plane itself. Okay, so the ground is going to be a boundary again. So I've got that. I've got that. X equals 2y. I'm just going to do this. I'm going to just divide both sides by 2. Y equals 1/2 x. I'm going to do this 1/2 x is y. That's a line. It has a slope of 1/2, so it should go something like this. That's it, right? I've got that. This is this y-axis. This is this line. And z is the actual plane itself, which is the ground. it's hard to see what our region looks like right now, because do y'all agree we have no like enclosed region? Like our region on the ground is not enclosed, because it really only has like this line and this line. So nothing is like completely closed off like the previous problem where we had the three kind of lines together, which gave us a nice type 1 bound or type 1 region. Here it's not clear. So what I'm going to do is I'm going to try and start looking at the 3D drawing. Maybe if I do the 3D drawing, it'll be a little bit better. I'll try this, X, Y, Z. Okay, we have the Y-axis again, which is this. We have this red line that has some weird little slope to it, like a very shallow slope. So I'm going to go like this. And then we have the ground itself, which is the XY plane. So I think we have no choice at this point but to look at the actual equation of the cylinder. So this is a cylinder, right, which has a radius of 2. And which axis does it go down?
Down the x-axis.
Down the x-axis, because x is free in the problem. There's no x variable. So this basically means we have a bunch of circles of radius 2, circles in the YZ plane, which means that they go down the x-axis. So we have, I'm just going to draw it real quick. We have like a tube that goes down like this, like that. Right now, that's not a very good picture. So let me ask you, on this picture here, it would be going down the x-axis. It would be hitting, right? Wouldn't it be hitting the XY plane somewhere, that tube? How could we figure out where this tube hits the XY plane? What could we do?
The radius of it would be 2.
The radius is 2.
So it hit it y equals 2.
Y equals 2 and -2, right?
Yeah.
On both sides. Do y'all understand? Now, really what we're saying is if we want to see this over here, just let Z be 0. If Z is 0, then you get y squared is 4. And that means y is plus or minus 2. And that gives us 2 new boundaries to look at. Here's up here at 2. And here's down here at -2. So we're trying to find the region enclosed by all of these things. Do y'all see it? Y'all see it right there? It's enclosed by the y-axis, by this line, and by this edge of the cylinder. Now, why not over here? Because would you agree this is also enclosed by all of them? The green one, the blue one, the red one?
Says
Why am I not?
First octave.
It doesn't.
Yeah. Yeah, I'm in first octane. Okay, it says it in the problem, I'm in first octane, which means that I'm going to not even look over here. So in my picture, let me go back to my 3D picture. I have parallel to the x-axis, I have a line going through like this. And there's my region on the ground. Hard to see it, but there it is. Oh, man. Okay. Let's try and see if we can do this without a picture. Is this a type 1 or type 2? It can be either, right? Either one. But type 1 seems pretty reasonable. Can you tell me what the restrictions on X are? Like, where does X start? Where does X stop?
Starts at 0 and ends at 4.
Okay, how'd you get 4?
Put it into the where x equals 2y.
Yeah, you basically want to
Y
know
equal
when
2.
is this red line going to hit the blue line. So you want to know when is 1/2 x going to be equal to 2. And that's when x is 4. So if x is 4, you're going to hit, these two are going to hit each other right there. So this is 4. So we have bound on X between 0 and 4. What about boundary on Y? Bounds on Y. What's the lower bound function? The red one, right? So the Y's are stuck between here and here. 1/2 X, right? That's the lower bound. And then the upper bound is what? Do I have to
Y
call it?
equals 2.
Y is 2. So our X's are between 0 and 4, or Y's are between 1/2 X and 2. So now let's talk about the surface. It's going to be hard to draw this, but can you tell me what the top of it's going to be? And then what the bottom of it's going to be? Start with the bottom. What's the bottom restriction on our solid going to be?
The XY plane.
The XY plane, which is Z equals 0, right? So this is the bottom is Z equals 0, the XY plane. What about the top one though? Isn't that the cylinder? Right? It's the cylinder. But see, the cylinder right now is written as this equation. In order for us to look at it as a function of X and Y, we need to solve it for Z. So let's isolate Z and take the square root. And when we take the square root, we get plus or minus. And we are going to throw away the -1 because we are in the first octant. So we're only concerned about the top part of this. That's your top. Z equals square root of 4 minus Y squared. And that should be enough to put it all together into an integral. It's a type 1, so I'm going to do double integral. My restrictions on X first, 0 to 4. Then my restrictions on Y, 1/2 X to 2. And then it's the top surface minus the bottom surface, which is 0, and then dy dx. Again, because X is the held between constants, it's the outer integral. Because Y is between two functions of X, it's the inner integral. That's it. We just have to do that integration. So if you had to integrate this with respect to Y, you kind of have two choices. There's probably a formula in your formula sheets to do this, or you would have to do trigonometric substitution. But I'm just going to say equals ... meaning you could all figure that out. Yeah. Or do you want me to take it? I mean, what do y'all want to do?
I haven't seen that in a while.
Yeah. Okay, so I'm going to my formula sheets and I'm going to look, do I have a formula that will allow me to integrate the square root of a squared minus x squared? Has to be a squared minus x squared. It's not on this formula sheet, I don't believe. Yeah, all right. We have a squared plus u squared. That would work if it was a plus between them, but it's not. All right, well, I'll work it out. Y'all ready? Let's do it. I'll start a new page. Okay, so on the side here, scratch work, I'm just going to try and figure out what this integral would be. And I'll come back and plug it in here later. So I need to make a trigonometric substitution. So I'm going to replace y with something. Let's see, do y'all remember what the trigonometric substitution is? If you have something that looks like a squared minus u squared or a squared minus x squared.
Is it cosine?
Cosine?
Like 2 cosine of theta? I'm just guessing.
You're just guessing?
It has to do with sine.
Yeah, let me see. I'm trying to see if my formula sheets, I don't think the formula sheets have it. I'm pretty sure they don't on the ones that you have for the class. It doesn't have them. Now I know my Cal 2 students, I give them a formula sheet that allows them to do the trigonometric substitutions. So, how do we want to do this? I'm just wondering, should I open the book? Maybe I can just tell you the reference page on the book. Is that okay? Just tell you where in the book it is. This would be in chapter 6. It would be under trigonometric substitution, which is 6.2. This would be on page 322 of the textbook. Remember, you can open up the electronic version of the textbook. 322, this is 6.2. This is called trig substitution or trig integrals. And there's a formula there, and it tells you what to do. If you see, it says, if you see the square root of a squared minus x squared, then the trigonometric substitution you make is x is equal to a sine theta. Cosine would work also, Caden, but sine is the standard one. Okay, so for us, we are going to replace y with 2 sine theta. And then we differentiate both sides, so we get 2 cosine theta d theta. And then we also realize that we can replace 4 minus y squared with 2 cosine theta. So I'm not going to spend a lot of time. I'll take that and just move it, just in case you need that up there. There we go. Okay, so I'm not going to spend a lot of time talking about why this is the way it is, because this is Cal 2 stuff. But it now allows us to rewrite our integral. And it becomes, this part right here becomes 2 cosine theta. And dy becomes 2 cosine theta d theta. And then we can pull out a 4, and we have cosine squared theta d theta. And then once we see cosine squared, we can do a half angle identity or a power reducing formula, however you were taught. But that becomes 1/2, and then 1 plus, anyone know? Cosine 2 theta, d theta. That's a half angle. I think that one's on your formula sheet. Right here, this one right here. Cosine squared of theta would be 1 plus cosine 2 theta over 2. All I did was brought the 2 out front as a 1/2. And then you can bring the 1/2 out. This is 2 integral, let's see, 1 plus cosine 2 theta d theta. And then 2, now it's time for the antiderivative. So the antiderivative of 1 is theta, and the antiderivative of cosine 2 theta is 1/2 sine 2 theta. And then plus some constant. Does this all look familiar from Cal 2? Now we're not done because we got to get everything back in terms of y. Right now our answer has theta in it. So we need everything back in terms of y. And on top of that, I have sine of 2 theta, which doesn't help because I only know about what sine of theta is. So here's where I would go and say, this is 2 theta. Now let me do it this way, 2 theta plus, I use the double angle identity for sine. So that becomes 2 sine theta cosine theta plus c. So just rewriting that to this identity, the 2's cancel. We get 2 theta plus sine theta cosine theta plus c. So that's where we are. We still need to get it in terms of y. So to get this in terms of y, the way I teach my students is I always tell them to go back to your original trigonometric substitution.
Wait, don't you distribute the 2 to sine theta, cosine theta as well?
Yeah, oh, these cancel. I forgot to put the 2 there. Yeah, those cancel and became a 1, but I forgot to put the 2 in front of it. Thank you.
Yeah.
Okay, so I go back to my original trigonometric substitution. And then what I do is I solve for sine theta. And that allows me to draw a reference triangle, where this is theta. And sine, by definition, is opposite over hypotenuse. So I can call this side y and this side 2, opposite over hypotenuse. I can always solve for the other side by doing, a squared plus b squared is c squared. I'm not going to show the work, but this becomes 4 minus y squared. And then the reason I do this is because I need to know what sine theta and cosine theta are. I know sine theta is y over 2, but I don't know what cosine theta is. But if I look at this triangle now, cosine is going to be the adjacent over the hypotenuse. So now I can do that. And we also need to know what theta is. So I take this and I do arc sine on both sides. So we have, finally, 2, and then arc sine of y over 2. And then plus 2, now sine of theta was y over 2, times cosine of theta, which is the square root of 4 minus y squared over 2. Okay, which is 2 arc sine of y over 2, and then plus a half y square root of 4 minus y squared. Plus c, plus c, plus c, plus c, plus c, whatever. So there it is. There's my indefinite integral. So that's what I'm going to plug in up here for my inner integral. Okay. Here it comes. I have integral 0 to 4. Okay, the antiderivative we just found was 2 arc sine of y over 2. And then plus, plus 1/2 y square root of 4 minus y squared. All of that evaluated from y equals 1/2 x to y equals 2. And then whatever we get here, we're going to integrate with respect to x. Wow, right? Wow. Integral 0 to 4. Okay, we're going to plug in now. So let's plug in 2 first. Plug in 2, I'm going to get 2 arc sine of, let's see, 2 over 2 is 1, so arc sine of 1, plus 1/2 times 2, and then square root of, oh, what's it going to be if I plug 2 in here? 0, right? 0. Okay, that's good. That makes me happy because that goes away. And then I have to plug in 1/2 x. So we're going to have 2 arc sine of, if we plug in 1/2 x right here, we actually get x over 4. And then we have plus, I'm going to definitely run out of room, 1/2. Let's see, y is 1/2 x times, and then I'm out of room, square root of 4 minus 1/2 x squared is 1/4 x squared. I'm looking at this and I'm like really kind of not happy about this. Okay, so arc sine of 1, what is that? At what angle is sine 1?
Pi over 2.
Pi over 2, so this is pi over 2. All right, so let me see if I can get a grasp on what we have here. 0 to 4. Okay, this part gives you pi over 2 times 2, so this is pi. And then that was 0, and then we want to subtract all this. So it's going to be minus 2 arc sine of x over 4. And then I'm going to subtract again. We've got to put these two together, minus 1/4 x square root of 4 minus 1/4 x squared dx. Oh my goodness.
It's gonna be another page.
Yeah, this is going to be horrible. Well, this one's actually not too bad. This integral, when we do this, this is a basic u substitution. Because if you let u be this, the derivative of that is almost this. So that's going to be basic. This one is the one that's going to be harder. The antiderivative of arc sine.
Would we have been able to avoid this if it would have been a type 2?
So I was just about to say, what if we had done this as a type 2? Would it have been easier integration? Possibly. I think it's worth looking at because this right here is not going to be fun. And I think back to Cal 2. Did you ever do this? You can do it. I mean, it can be done. Look, I'm just going to show you. I think I'm going to come to a point where I'm going to stop here because it's just going to take up way too much time. We're already almost halfway through class. So look, if I had to integrate arc sine of, let's just say x, then I would do integration by parts. I would do that u is the arc sine of x, dv would be dx. And then when I take derivative of that, I get 1 over the square root of 1 minus x squared dx. And when I integrate that, I get x. And then when I do those two in the new integral, I can do a basic u substitution. So it is possible to do that integral. It's not what I feel like spending 30 minutes on. Now, to answer Adam's question, let's go back. If we were to have done this as a type 2 instead, how would that have helped? Well, now restrictions are on y. Y is between two constants. What would they be? So I'm looking from here to here, right? Y would be between 0 and 2. What about our x's? Our x's are stuck between the left side here, which is 0, and the right side, which is this red graph, but solved for x, not for y. What is this red graph solved for x? 2y. Okay. And then the top and bottom surfaces don't change, do they? So we'd still have this, but our limits of integration would change. So it'd be integral 0 to 2, integral 0 to 2y. I have square root of 4 minus y squared, still the same, but now dx dy. Are there any questions on the type 2 setup? So Adam, you asked, would this be easier, right? Is it?
Yeah.
Does it appear to be easier?
I would say the first one is going to be easier, but then the second one is just going to be just as hard.
Okay, let's see. If we do the first one, what's the antiderivative of all of this with respect to x? See, now we treat all this like a constant, right?
It's x.
So this is going to be x times the square root of 4 minus y squared. That's the antiderivative, right? Of this with respect to x. And I evaluate that from x equals 0 to x equals 2y. You see, there was no trig sub here. Very nice, right? Now replace x with 2y and then replace x with 0. So if we go integral 0 to 2, let's go 2y right here for x. We get 2y square root of 4 minus y squared.
Oh, and then it can be u sub.
Plug in 0 and we get nothing, right? So this is it. This with respect to y. And that is easy to do because I can just do a u sub, right? If I have to do 2y square root of 4 minus y squared dy, and I'm doing a quick u sub, u is 4 minus u is 4 minus y squared, du is negative 2y dy. I almost have negative 2y. I just need to change the sign. So I would go negative du, positive 2y. So this integral becomes what? This right here is square root of u. And the 2y dy gets replaced with negative du, which is the integral u to the half du. And this is going to be negative 2/3 u to the 3/2. So this is just basic u sub. So this becomes negative 2/3 4 minus y squared to the 3/2 evaluated from 0 to 2. I'm almost there. I may as well just finish this. If I plug in 2, what happens?
Turns to 0.
I get 0. So when I plug in 2, I get 0. And then I take away from that whatever I get when I plug in 0. When I plug 0 in here, I get negative 2/3 and then 4 raised to the 3/2. And 4 to the 3/2 is the same as square root of 4, which is 2, and then cubed. So this is just 8. This becomes positive 16/3. So to answer, I don't know who mentioned changing the integration as to a type 2. Was that you, Adam?
Yeah.
Yeah. So I was just, when we got to this point on the previous work, when we got to this point right here, I was gonna say, right when we got to this, would it matter if we change the order, like the type 1 to type 2? Is it gonna make our integration easier? Not necessarily, but it could. And I might have, now that we've been through this, maybe at this point in the beginning, you start saying to yourself, you know what, let me see if I can do it type 2. Maybe this integration will be easier and avoid all of this. But I think this was a good exercise, don't you? I think so. I feel like we should check our work. So watch, I'm gonna go to Wolfram Alpha, integrate. It was the square root of 4 minus y squared, right? Integrate that. And what was the restrictions on y? It was from 1/2 x, right?
Yeah, 1/2 x to 2.
So x is 2. Oh, so y is 2?
Yeah.
Okay, let me see what it does with us. Standard computation time exceeded. It's having trouble with even the inner integral. I guess I have to be pro to do this, I guess.
Standard computation time is 1 second. So if it
Oh,
takes
is it? Yeah, but they want, pro means I have to pay, right? I'm not doing it. So I'm surprised it couldn't handle that.
probably use the like Desmos one.
Yeah, I'm just gonna use my actual Mathematica program, which is so much easier to use. So here's how the Mathematica program works. I just go to, where is it? Here we go. So I want to do some integrals. I'll make this big so y'all can see this. Oh shoot, where'd it go? Here we go. Make it so you can see it bigger. Okay, so I can do an integral, and then inside that I'll do another integral. So double integral. So the first one we had 0 to 4, right? 1/2 x to 2. And it was the square root of 4 minus y squared. And we did with respect to y, then x. See what it does. Should get what, 16/3. There we go. Now watch, if I just take the inner integral. Oh, whoa. That's the one we did and we stopped after this, right? There it is. So there it is, pi minus 1/8. I think we had something like this. I think we had a 4 here, didn't we? And then we had an arc sine. So this, I mean, there's some identities that they may have used that are different, but yeah, so there's a lot of craziness happening here. So if we change it, you know, change the integration order and stuff, it's easier for us to do. The computer got it right away, but all right. I think done. Oh, y'all want to see it? You don't want to see what that one looked like, just so we can see it? So this is it right here. We had the cylinder coming down the x-axis, and then we had the different planes that were cutting through. So we had the ground, we had the y equals 0, or sorry, x equals 0, and then we had that y equals 2x, or 2x equals y. What was it? Y equals 2x. X equals 2y. X equals 2y. There it is. So we found the volume of that solid right there to be 16/3. 16/3. Yeah. All right. So, you know, there's a cool problem that comes up. I think is an interesting problem to look at. If I do intersection 2 pipes. So if you look at 2 pipes coming together like this, and you wanted to know what the volume of these 2 pipes were together, right? Then if I asked you for the volume of one of them, you could do that, right? But the fact that they intersect means that there's some region inside of them that they share. And so you can't count that. You know, you can, if you do the volume of each pipe separately and then add the 2, you've double counted what they have in common. And so a good problem would be to try and figure out, you know, what the volume of the intersection of 2 pipes is. So you have to figure out a way of representing this solid and finding its volume. And you can do it with what we're doing right now. We have a lower, you know, we have a domain, we have an upper curve and a lower curve, or lower function surface, and you can actually figure out that common volume that they share. I'm not going to do it. There's a problem in the book like it though. All right, we need to move on. You all happy moving on? Okay, we are going to now do double integrals in polar coordinates. So polar coordinates is something that you're supposed to cover in Cal 2, but I know that every class is different. Some professors don't get to it. I sometimes do, I sometimes don't. It just depends on the semester, how many holidays are in the semester, how well my students are doing. So it's okay. If you have never seen polar coordinates, I think it's easy to pick up. Okay, I think so. At this level, it's easy to pick up. You learn it in pre-cal, it's a little different, but now you're hardened math students by this point. So double integrals and polar coordinates. So far, we've done these 3 types of regions. We can do double integrals over rectangles. We love those because our x's and y's are both between constants. And then we even said that the order of integration does not matter. And those are super easy ones. Then we have type 1, where the x's are between 2 constants, g's are between 2 functions of x. There, the order does matter. And then type 2 is the other way around, right? Y is between constants, x's are between 2 functions of y. But what if we have a different type of region that doesn't look like any of those, right? So this is where polar coordinates come into play. So first, what are polar coordinates? Well, remember that if you're given any point in 2-dimensional space, right? In 2-dimensional space, if I give you any point x, y, the x is the x, how far you go on the x-axis, the y is how far you go up or down. But if we do this and draw a right triangle, then for every given point that we have, there will always be an angle that we can form, right? That an angle from the x-axis to this line, from the center to that point. And we can also calculate the radius, which is distance from the origin to that point. So for any point you ever give me, you can either give me the x and y coordinates, and I can go to the point, or you could give me the angle and the radius. The way I look at it is this, and it's much easier if we're like in a classroom. The XY coordinate system is what's called Cartesian. I think I'm spelling that right. Is it A-I-N? Where's my English people? Cartesian? Doesn't look right.
Oh, that's right.
That looks right.
I hate the English language. I look at words sometimes, I'm just like, that can't be the right spelling, but okay. So Cartesian coordinates are your standard XY. So if you want to go somewhere, you start at the origin. I give you the X, it tells you how far out to walk. And then the Y tells you whether or not you're going to go up or down by an amount. And once you're there, boom, you're there. Okay. Another way you could get to that point is to start out at the origin, face this direction, and then instead of telling me the X and Y, give me the angle. I will rotate by that angle, theta. So now I'm facing this way. And then just tell me how far out to walk, right? And I will still land at that point. So it's just two different ways to look at points within a plane. Either Cartesian, which is the X and Y, or polar, which requires you to give me the R and the theta. And so hopefully this makes sense off of this picture, that the X coordinate would always be R cosine theta. That you can get by just looking at your standard trig functions. And this you should have talked about in pre-calc, right? The X is R cosine theta, the Y is R sine theta. So that's the general idea behind polar coordinates. Now we have some relationships between Cartesian and polar. So if you have Cartesian coordinates, there's an easy way to turn them into polar, or if you're given polar coordinates, there's an easy way to get to Cartesian. And here are the relationships we have. And I think that they're obvious from the picture. Right, the first thing is the relationship here that if this is a right triangle, Pythagorean tells us x squared plus y squared is r squared. So we have that relationship. We also know that the x coordinate is r cosine theta. We know that the y coordinate is r sine theta. And if we ever needed to recover what theta was, if you give me the y and the x, I can do arctangent to recover the theta. So those are our standard relationships between Cartesian and polar. And the whole idea here is that sometimes it's better to be in Cartesian, sometimes it's better to be in polar. It just depends on what you're trying to do. All right. So now I want you to think about a rectangular region back in Cartesian. So remember I said that in Cartesian, if I do AB cross CD, that this meant all the points where your X is between two constants and your Y is between two constants. My question for you, and I want you to think about this for a minute. I'm going to let you think while I refill my drink. I want to know, what would this look like? If I'm in polar coordinates, okay, so if we're looking in polar coordinates, what would all of the polar points r theta look like if I told you that the theta is between two constants and the r is between two constants? So it's the same as Cartesian, x and y between two constants, but instead of the x and y, I'm talking about the r and theta. Think about it, and then I'll show you what it is. And yeah. Okay. Y'all ready to see it? There it is. This is what a rectangle looks like in polar coordinates. A rectangle meaning that the radius is stuck between two values. So I've got all the points. Right now we're looking at all the points where the points are all stuck between two circles. Right? Oh, sorry. So you have like an inner radius, which I think we called A, is distance from here to here. And then B is the distance from here to here. So far, all the points in this dark region, do you agree, have a radius between A and B? And then as far as angles, well, all the points are either between this angle, this right here, which is alpha, or this angle here, which is beta. So every point that lies in this region has an R between A and B and an angle between alpha and beta. Make sense? So that's what a rectangle looks like in polar coordinates. It doesn't look like your standard rectangle, right? A Cartesian rectangle looks like that. This is what a polar rectangle is. So if I start making adjustments, like I can change the A, right? I can change the A. What if we make A 0? That's the inner radius is 0. Then we get this like slice of a pie, right? I can change the angle. Swing the angles around, right? Wherever I want. I can make this come in. So any region that you can think of that has this sort of shape to it would be a polar region. In fact, what about if we go all the way around that, bring A back to 0? There you go. A disk, right? This disk would be a polar region. Here, what would be our restriction on theta? What's our theta stuck
Pi.
between here?
0
to
and
pi.
360.
Yep, 0 to 360. And then the radius would be stuck between 0 and whatever you want your outer radius to be, right? So when I have a region like this, when I have a region like this, I definitely would not, if this were my region, I was trying to find the volume of a solid or something above this, I would definitely not be able to do this using rectangles, Cartesian rectangles, or type 1 or type 2. Do y'all agree? This won't qualify for any of those. We can only do a region like this with polar. So now it becomes a question, how do we do it, right? Like, how do we actually do a double integral? So remember in Cartesian, the whole idea here was that we had a surface and the dA represented this infinitesimal little area, patch of area on the ground, right? That's what it was. Now what we want to say is what is dA? What does this little patch of area on the ground look like in polar coordinates? So this is a little bit tricky because this is not a nice rectangle. So it's not just like dx times dy, like we can't do that here. What we can do though is we can try and treat this almost like a rectangle. So you have to imagine that if this got like infinitesimally small, like super, super small, then it basically is a rectangle. And so all we need to know is how long this side is and how long this side is. Well, this right here, remember R controls the out, the spacing, right, between the two, the inner and outer radius, the R is controlling that. So if I make a little small infinitesimal change in R, this should be dr, right? Just like over here, This width was a little infinitesimal change in X, so we call that dx. Same thing here, this would be dr. And this right here, a lot of people think that this is d theta, but it's not. Okay, because theta is an angle measurement. So if theta changes just by a little bit, this right here is r d theta. Do y'all know where this comes from? Do you know why that's r d theta? If this little change in theta, d theta, little infinitesimal change in theta is d theta, then why is this length r d theta?
I'm guessing because of arc length.
Arc length, exactly. If you go back and you remember from pre-cal, there was a formula, S equals r theta. This was a formula that said if you have start at the origin, go out to some radius, and then start swinging through some angle theta, that if you want to know S, which is this length of this arc, it will always be r times theta. So if we're trying to figure out the length of this little arc right here, we need to know how far we go out. Well, we go out r, and then the angle that we swing through is just a little infinitesimal change in theta. So if you multiply those together, you get r d theta. So if we want to know the area of the whole thing, the whole little patch, then we're going to do the dr times this, and that's where this comes from. So why am I showing you this? Because if you're going to be doing a double integral in polar coordinates, you don't have dx dy like we did with Cartesian. What you have is either r dr d theta or you have r d theta dr. It's one of these two. And so the next note is very important. For double integrals over polar regions, if your region R is all the points, polar points, where theta is between two constants and R is between two constants, then the volume double integral that we've been studying turns into a new double integral where your limits of integration are your limits on theta and r respectively. You have d theta dr at the end, but then I've highlighted you must throw an r into the integral. You must. If you forget that, it's over. And then your function, instead of being a function of x and y, see what we've done is we replaced x and y with their polar equivalents. Okay, I think it's always best to just see this in action. Find the volume under this surface, z equals 3x plus 4y squared on the region bounded by x squared plus y squared equals 1, x squared plus y squared equals 4 with y greater than 0. All right. Let's try and see what this region that we're integrating over looks like in 2D. And then I'll try a three-dimensional if I can, but let's see. Our region is bounded by x squared plus y squared equals 1. That's a circle of radius 1. X squared plus y squared equals 4, which is a circle of radius 2. And y is greater than 0, which means that we can't be looking at the bottom half. So we are only looking at this region right here. That right there. That's our domain. And what we're doing is we're saying, what is the volume underneath this surface on this region? So I don't even think I need a 3D picture because I know this surface. I need to basically do the double integral of this surface over that region. I should be okay. But because my region is polar, I need to put restrictions on and make this a polar integral instead of a Cartesian integral. So to do polar, I need restrictions on theta and r. So what are my restrictions on theta and what are my restrictions on r for that region? Let's see, last time I called on Terrence. How about Margie? What do you got, Margie?
Theta has to be between 0 and pi.
Good. And radius?
Radius has to be between 2 and 4.
I think the inner
No,
one was
not
1, right? It
I'm
was
sorry.
1 and 2. It was
Oh, 1 and 2. 1 and
X
2.
is 1, that radius is 2, so 1 and 2. Everyone
Yes.
agree? That's it? Okay, good. Now, according to the formula I just gave you, if we're gonna convert, right? If we're gonna convert, then we need to do a few things. Let me erase this. So if we're going to do this, Margie, we're going to do the double integral over the region R of the surface with respect to area. But because we're going to polar, we're going to go integral from A to B. So let's go ahead and start doing that. So we'll go integral. Let's see. So what limits go here, Margie? I think you're on mute.
Oh, sorry. Sorry, it's going to be from 0 to pi.
Okay, so
It's on-
the outer ones go with R, right? So what's our restriction?
Oh,
on R?
Okay, so yes, but so for the outer ones is going to be between 2 and 1. So 1 and 2
Yep. And then the inner
And then-
ones,
between 0 and pi.
okay, everyone okay with that? Now, Margie, this is the part that you just have to remember. We're going to do the original surface, the function, right? But we have to replace X with this and Y with this so that everything is in polar coordinates. So this
Okay.
is our original surface.
Mhm.
If I replace X with this and Y with this, what would I have inside this integral?
Let's see. So you're going to have 3. So you'd have 3, and then you have to open your parentheses, r cosine
Mhm,
of theta.
okay.
And then,
That would be this.
right. And then the second part would be 4
Mhm.
sine squared of theta. I'm sorry.
Yes.
No, it'll be, yeah, 4 and then sine squared of theta.
Yes.
Or would be
And then
r
I'm going
sine.
to just square them both.
Yeah,
So I'm just
exactly.
going to square the R and the sine and get this.
Mhm.
Good. That's it for the function, right? Any questions on that, anyone? Okay, Margie, you're almost done. What's next?
Okay. Well, then you're going to go ahead and get your integrals.
Okay, so what do we did this part.
Mhm.
What are we missing still?
Oh. Okay, so you've done that part. So then you have to,
We've done that part.
oh, okay.
Because
Oh,
we're going
even
from
Yeah.
because we're going from Cartesian to polar, you must always, 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 always have an R in there,
Mhm.
all right? And then you can do your d theta dr.
Yes. So
Okay,
now for
good.
that R, do you have to go ahead and are you integrating it from 1 to 2 as well, or is it all? It's all part of that, right? So do you
It's
have
all part
to
of
have
it.
extra parentheses?
I'm just going to
Okay.
basically distribute it through.
Oh, okay.
You just distribute it here and here.
Yes,
So
and
it's just gonna
that'll
multiply.
simplify it.
Yeah, this will become 3r squared cosine theta
Mhm.
plus 4r cubed sine squared theta, and then d theta dr. All right, good, Margie, thank you. Now we'd have to do this integral. So, we'd first start off in here doing the integral. So you'd have to integrate this with respect to theta, treating r like a constant. So you'd have to do antiderivative cosine, which is sine. Sine squared. You need to do like power reducing formula on this. So I'm not going to continue these because we just don't have time to take these the rest of the way. But we could do this, all right? The big thing is the setup, making sure we get the integral right. Now, visually, just so we can see what we just did. So there was our domain, right? There was our domain. I don't know why this is so small over here. There's our domain, three-dimensional space. And then we have our surface. And then we have the solid beneath it, which is this. And let me take the surface out. There it is. Kind of a cool looking surface, or sorry, volume, solid. See how some of it's below the XY plane? That volume is counted as negative, remember from last time? And, but our total volume would be whatever that answer is. Now, look, I mean, on your final exam, I am gonna have you calculate some of these double integrals all the way to the final answer, but only like one of them probably. Most of this is just gonna be set up. Like set up the integral and that's it, be done. Because we just don't have time during a test to do this. And we all know that in reality, I mean, we have computers to do the computation part, like the 16/3 that took my calculator all of, you know, half a second to figure out, right? So the thing that the computer can't do is translate the problem into the math. Once we get it to the math, the computer can kind of take over for us. Okay, let's do breakout rooms. And I want to see if y'all can figure this out. All right. So please make sure you copy this down real quick. And then I'm going to put you in breakout rooms. Join whenever you've copied it down. It's 2:18. Let's go right till about 3 or 4 minutes before the end of class, maybe 5 minutes. All you're trying to do is set it up, okay? Don't worry about doing the actual integration. Just see if you can set up the integrals. There you go. So the breakout rooms are open for you. Okay, just waiting for the group from room 1 to come in. Twenty seconds. Okay, I think everyone's back now. I was able to talk with all groups about this, and I think the struggle was finding the radius of this region on the ground. And so because it's a disk, it definitely goes from 0 to some radius. And to figure out how far it goes out, you have to figure out where these two surfaces intersect one another. So you either set them both equal to 0. Hold on. You either set them both equal to 0, I mean, not equal to 0, sorry, equal to z and then solve, or you can just take this value for z and plug it in right there. So if you square that, you get x squared plus y squared here, which is this. And then if you just start grouping things together, you get 2x squared plus 2y squared is 1, divide both sides by 2. And now you have the equation of a circle, and that circle has a radius of the square root of this, which is 1 over root 2. So you know that the theta swings you all the way around, and your radius is from 0 out to 1 over root 2. And so the only thing left to do is to figure out what these two pieces are. The top surface minus the bottom surface. So you still have to go in here, solve this for z. That's already solved for z, but then you have to go and convert it to polar, which I think I'll do that at the end of class. Try it yourself, but I mean, when I come, sorry, I'll try that next class. I'll start with this, but there's still some work to do, all right? Okay, that's gonna be it for the week. I owe you a mini exam, so be looking for the next mini exam to be sent out here in the next few days, and that way, I don't know if I'm gonna be able to get all 8 out before the semester, because remember we lost that week, so I'm not sure if I'll be able to get all 8. We'll see. But yeah, that's it. You got any questions?
The mini exam, it wasn't the well, it was technically the second one, but you gave us like an extra one.
Yeah, lines and planes.
Yeah, the lines and planes. Are you
Yeah.
still gonna, is it still grading or?
Yes, I will take care of that. Yes.
Okay, all right.
Yeah.
Awesome.
I know some of you turned it in. I will give you a grade for that. No worries. Okay.
All right.
All right, everyone. Have a good weekend.
You too.
You too.
Thank you.